So last time we learned about the Fourier-Motzkin algorithm, which basically tells us how we can project a polyhedron on a smaller dimension. So let's say I have a polyhedron in n dimensions, then I can remove one dimension, say the nth dimension, and project the polyhedron on the remaining n minus 1 dimensions, and how one could do this by just manipulating the inequalities that represent that particular polyhedron. Now, so the bigger problem, however, is that given a polyhedral iteration space, a polyhedron S, generate a loop nest with a certain arbitrary order of the loop iteration indices. So let me say that order is x1, x2, xn, where x1 is supposed to be the outermost loop iteration index and xn is supposed to be the innermost loop iteration index. Now, the original polyhedron is just a set of inequations. Maybe it is constructed by by an original loop nest which had a completely different order of these loop iteration indices. We don't know what that original order was. We don't care what that original order was. It was some arbitrary order of loop iteration indices, and now we have abstracted that order of indices into a loop of a polyhedron, into a polyhedral space, and now we want to redefine the order, and we have chosen our own arbitrary order x1, x2, xn, and we want to represent that polyhedral space in this particular order. Now, of course, I can only kind of change the order of indices if I'm respecting data dependencies. So far, I have not really delved into the question of what are the data dependencies, how do I kind of preserve data dependencies and so on. But let's just assume that either there are no data dependencies, or even if there are data dependencies, when we do this kind of reordering of loop iteration indices, the data dependencies are being respected. But even, we forget about data dependencies. The question is, if we have this order of loop iteration indices, what should be the lower and upper bounds of each of these loop iteration indices? And this is something that the projection algorithm, the Fourier-Motzkin algorithm, actually helps us determine. And so here is the basic idea, that we start with the innermost loop index, which is xn, and we bring the inequations to the form L is less than equal to C1xn or C2xn is less than equal to U. And this is exactly how the Fourier-Motzkin algorithm also proceeded, where C1 and C2 are positive coefficients of xn. And now once we have that, using these inequations, we can project, and of course there will be some inequations that don't involve xn at all, and so even that forms the part of the projection, and we project on the remaining iteration dimensions or iteration indices x1 xn minus 1, and we use the Fourier-Motzkin method to do that, as we saw in our last lecture module. And once we have projected it on the remaining set of indices x1 xn minus 1, we can now recursively do this. So from that polyhedron, now we get a new polyhedron S prime, and from that S prime we can now remove xn minus 1 to project on the first n minus 2 indices, and keep doing that as we go along. But now, till we get to the first iteration index, which is x1, and from that we will know what are the bounds of the outermost iteration index x1. It will be only constants, 0, it will be some constant, it will not involve any of the other loop iteration indices. And once we have the bounds for x1, we would want to know what are the bounds of x2 in terms of x1 and potentially other constants. And to do that, we just use these inequations like L is less than equal to C1 into xn and C2 xn is less than equal to U to determine the lower and upper bounds for xn. So at every step, when we project and remove one iteration index, when we have kind of figured out what are the inequalities that represent the projected polyhedron, for the iteration index that was just removed, we can determine the lower and upper bound by exactly these equations that we used for the Fourier-Motzkin method. Alright, so for example, we can just say that xn should be greater than equal to L by C1 and xn should be less than equal to U by C2. Recall that L and U are just affine expressions on x1, x2, xn minus 1. And so this basically gives us lower and upper bounds on xn. To see this with an example, here's our code for I equals 0 to 9, I plus plus, for j equals I to till j is less than 7 and j is less than I plus 4, j plus plus, and then there's some loop body, aij equals 0 in this case. Now the desired order was j comma I. So what do? I start with the innermost loop index, which is I, and I try to remove it and project on the remaining loop indices, which in this case is j. And so I basically bring my equations or inequations into the form which is, because xn in this case is I, so I say 0 is less than equal to I. So here L becomes 0 and the coefficient of I is just 1. Similarly, I is less than equal to 8, so U becomes 8. I is less than equal to J, that's coming from the fact that J starts from I, and so now U becomes J. I is greater than equal to J minus 3, so L becomes J minus 3. Okay, and now once we have done this, we project on J, we do a projection on x1 dot dot xn minus 1, which in this particular example is just a single variable J, and we get J is greater than equal to 0 and J is less than equal to 6. This is similar to what we had done in a previous module. Now once we know the bounds for J, we want to also know the bounds of I, and that just comes from these inequations which are already expressed in the form of L and U. And so from here we know that for given J, for a given value of J, we know what are the bounds for I, which is our xn in our general algorithm. So we know that I should be greater than equal to J minus 3, and so the lower bound of J, and I should be greater than equal to 0. So the lower bound is maximum of J minus 3 comma 0, because that's just coming from these inequations that we constructed for our Fourier Motzkin method. Similarly, I should be less than equal to 8 and I should be less than equal to J. So upper bound is nothing but minimum of 8 comma J. But recall that we know that J is less than equal to 6. So minimum of 8 comma J is nothing but just J, because 8 is greater than 6. And because J can only take maximum value 6, minimum of 8 comma J is nothing but J. And so, we may or may not simplify it to J. We can just leave it as minimum of 8 comma J. It's up to us. But whatever it is, we have been able to identify the lower and upper bound of the variable that we just removed, which is xn, using these inequations. In this particular case, xn was I. And so this is the general method to be able to reorder the iteration space using any order of loop iteration indices. I can choose any order of the loop iteration indices and then apply the Fourier Motzkin method to do the projection. And once I have projected, I can also use these inequations to identify the upper and lower bounds of the inner index based on the fixed values of the outer indices. Okay, so we now can choose the order of iteration indices provided we respect data dependencies. All this discussion is basically under the caveat that we have been able to preserve data dependencies. Perhaps there are no data dependencies. We have not been talking about data dependencies. And in the 2D space, the fact that we can reorder the iteration space any way which we like, in 2D space is equivalent to saying either we can traverse the iteration space horizontally, which is something like this, or I can traverse the iteration space vertically, which is something like this. All right, and assuming I'm respecting data dependencies, it is really our choice in what way we basically traverse the iteration space. Depending on our choice, we can use the Fourier Motzkin method and the algorithm we just discussed to be able to identify the lower and upper bounds of each of the loop iteration index. Now here's one interesting thing about this. It's not just true that we can choose to iterate horizontally or vertically. We can actually choose to iterate in any direction we like, as long as the set of indices are such that it covers the entire space. For example, we can also traverse in the 2D case the space diagonally. For example, I can traverse something like this, and then this, and then this, and then this, and so on. And so what does it mean? And how do we do this? This is nothing but, this basically means that I want to change my axes from, let's say, I comma j or j comma I to, let's say, j minus I comma j. So which means that I would, this is my execution order, that lexicographic order. So I'm going to first do, increasing lexicographic order in the order of j minus I comma j. And this order will be different from I comma j or j comma I or any other kind of combination of axes. We just change the axis, and now we are going to, and the order is going to be defined by the increasing lexicographic order of the changed axis. But the question is, if I want to change the axis, how do I now identify what are the lower and upper bounds of the new axis? And the algorithm would look very similar to what we have already discussed. Basically, if I wanted to do j minus I comma j, what do I need to do? I need to introduce a new variable k to represent that new axis j minus I. So k equals j minus I. and now the desired order is nothing but k comma j, and now I rewrite all my inequations in terms of k and not in terms of I. Notice that there is no I here, and so I can eliminate I by saying I equals j minus k. So basic idea is that I will replace I with j minus k in the inequations. I'll get a new set of inequations, and I'm going to use the same algorithm which involves the Fourier-Motzkin algorithm, the method, to basically identify the lower and upper bounds for both k and j. Notice in this case I want j to be the inner index and k to be the outer index. So here's my original polyhedron. Here's just an example to show how this will be done. Here's my original polyhedron. Let's say I is greater than or equal to j minus 3, I is greater than or equal to 0, I is less than or equal to j is greater than or equal to 0, j is less than or equal to 7. This set of inequations basically specifies a polyhedral space in in 2 dimensions, I comma j. And in this particular case, actually, I'm using j comma I because if you notice, all the inequations, lower and upper bound of j are just specified as constants, and all the lower bounds and upper bounds of I are represented as functions of j. Okay, so these form the outer loop, and this forms the inner loop. Now I want to change the axis. I want to change the axis to j minus I comma j, or in other words k comma j. And what do? I rewrite these inequations to eliminate I, so that I becomes j minus k, and so I is greater than or equal to j minus 3 becomes j minus k is greater than or equal to j minus 3. I is greater than or equal to 0 becomes j minus k is greater than or equal to 0, and so on. I is less than or equal to j becomes j minus k is greater than or equal to j. And then everything which does not involve I just remains identical. J is greater than or equal to 0 and j is less than or equal to 7. Now if I just simplify these inequations, I get the following inequations. Some of them just become vacuously true, and so this becomes k is less than or equal to 3 and k is less than or equal to j. So this notation k is less than or equal to 3 comma j basically means that it's less than or equal to both 3 and j. In other words, it's less than or equal to minimum of 3 comma j. Similarly, k is greater than or equal to 0, j is greater than or equal to 0, and j is less than or equal to 7. So this is my new set of inequations, and I want to traverse this space, this polyhedral space, in the lexicographic order of k comma j. What is the innermost index? It's j. So what do I project on? I project on k, and from that I basically get upper bounds and lower bounds of the outer loop on k, and then I get the lower bound and upper bound of the inner loop of j for a given value of k. So I project on k by eliminating j. These are my equations that are that are in the form of L and U. So something into k is greater than or equal to L. Something into k is less than or equal to U. In this case, for example, j forms are U. Here j is less than or equal to 7 does not even involve k, and so on. So these are my set of inequations. I project on k by eliminating j. And so I get k is greater than or equal to 0 and k is less than or equal to 3. So I get this from my Fourier-Motzkin method. And for a given value of k, I get the lower bound and upper bound of j by just using these inequations. So the lower bound of j is maximum of 0 comma k, and the upper bound of j is 7. And so with that, I have been able to rewrite my loop in the desired order, which is k comma j. Recall that k is a change axis. It's basically j minus I. So for k equals 0, k is less than or equal to 3. The bounds have been determined using the Fourier-Motzkin method, k plus plus. For j equals 0, j is less than or equal to 7, j plus plus. And now I need to write my body. And recall that the original body was basically in terms of I and j, but now I is no longer present. Recall that the original body here was nothing but I comma j equals 0. I need to also replace I in terms of, or represent I in terms of k and j, and that's just going to be j minus k, because recall that k equals j minus I, so I equals j minus k, and so this is my new loop. It basically traverses the iteration space in a different order, but it is functionally equivalent to the loop that we had on the original slide.